Hello and welcome again to the J-Axis on YouTube. Here today to talk to you about one of my originally discovered math patterns, which I call numerical symmetry. And symmetry is a very important aspect of geometry, and as we know, we need arithmetic within geometry in order to, make up the equations that find things like surface areas and volumes and axioms and different measurements like that. So today we're going to see how not only does geometry happen, or arithmetic happen within geometry, but geometry actually happens within arithmetic as well in the form of numerical symmetries. First one that I think we should discuss is reflectional symmetry, because reflectional symmetry is probably the easiest one for people to perceive. And of course, that occurs when the line of symmetry causes each side to be inverse to each other. It's the type of symmetry that our bodies have. You know what I mean? They call it bilateral symmetry in biology. The way that it appears within reflectional symmetries, I'm going to show in different slides how this happens. And as we look at these patterns, if we imagine that there's a line of symmetry between these digits, or the letters that are representing what the digits could be, they're the same forwards and they're the same backwards. They're inverse to each other, meaning that a line down the middle of them would cause a symmetrical line of reflectional symmetry. And in all of these patterns, prime 11 always works, no matter the value of A, B, nor C. And that is why I believe that prime 11 is actually a governor of this particular symmetry. And it is the number that sort of controls and governs how this symmetry appears within mathematics as far as arithmetic and geometry. And really any number that has an even amount of digits and is the same forwards as it is backwards, almost like a palindrome that you see with words, it's always going to be divisible by 11, no matter what the number is, no matter what the digits are, their values. It's always going to be divisible by 11. It has an even number of digits. It's the same forwards as it is backwards. Next symmetry we should do is translational symmetry. Translational symmetry sort of moves in stacked waves or cycles. A good example of it is a checkerboard. If you look at a checkerboard from any angle, as far as the surface edges, it's always going to display translational symmetry, as in white, black, white, black, white, black in the squares, no matter which way you're looking at it. Alright, so let's see the different numerical symmetry patterns and how they appear with translational symmetry. As we're looking at these patterns, we can see that they're moving in waves, or they're moving in cycles. Some of them are 2 cycles of 3, or 1 cycle of 6. 6 cycles of 1, apologies. And they're all conveying translational symmetry in the same way that the last patterns were conveying reflectional symmetry. And all of these patterns are always divisible by prime 13, no matter the value of A, B, nor C. That's why I think that prime 13 is the governor of translational symmetry within math and geometry. And if you pay attention, you can see that some of the patterns that were within prime 11 in reflectional symmetry are within this one as well, and that's because the pattern can be perceived either way. It can be perceived as reflectional and translational, that's why both prime 11 and prime 13 will always work in these patterns. Alright, next time with symmetry we're going to talk about is rotational symmetry. And you see rotational symmetry within types of platonic shapes, whereas in like a triangle, if I were to take a triangle and rotate it to the other side, it would still be the same exact shape. So it has rotational symmetry. And in these numerical symmetry patterns, we can see them. And if we imagine like the AB pattern as if it was rotating on a belt, or any of these patterns really as if they were rotating on a belt, but this particular one, if we imagine it that way, like the first A moved to the back and it became like a BA problem, really that's not what it is. It's just another AB problem. So no matter how many times it rotates, it's always creating the same type of numerical symmetry pattern. And these patterns are always divisible by prime 3, no matter the value of A nor B. And we can also see helical symmetry happening within one of these patterns, which is just a different form of rotational symmetry, but helical symmetry more creates a spiral. And we see that in the pattern where it's A, B, A, B, B, and it just continues with each iteration to just add one more to the sequence, almost as if the digits are spiraling outwards as the pattern gets larger. So that's conveying helical symmetry, which is just a different form of rotational symmetry. And prime 3 always works in those patterns as well, which is why I believe it governs rotational type of symmetries, math and geometry. All right, so this is the part where if you haven't broken out a calculator, you might want to at this point, because we're going to talk about scale symmetry and prime 7. And this is where things can start to really get crazy. So scale symmetry occurs when two shapes which are similar overlap, and in their overlap they can be perceived as one shape. And you can see this if the reason it has scale in there is, imagine if there's a circle with another circle inside of it. You can perceive that to be two separate circles, but if you perceive it to be a whole shape and just the one circle, it still counts as scale symmetry, because it's the same similar shape even though their scale is different in their overlap. And the way that we're going to see prime 7 accomplish this is it's going to appear in 6-digit or less patterns as multiples of 7 in different mathematical sequences and constants. And these multiples are going to overlap to completely compose these patterns. And in that overlap of these multiples of 7, we perceive these what seem to be one whole number of a sequence or an infinite decimal. So start sharing them now and kind of give a few seconds for each one to look at if anybody wants to pause or check this out with their calculator, because it is kind of crazy. I'm going to show like the prime number sequence, how prime 7 accomplishes scale symmetry with that. And of course we have the golden ratio, which is also the phi decimal, and that's what is actually written out here. And we have the Fibonacci sequence, and we're looking at the sequence as if it's one long number, and how treating the sequence this way makes these multiples of 7 appear in these patterns. We'll move on to the Padovan sequence, which, just like the Fibonacci sequence, actually creates the golden ratio spiral that we saw in the phi decimal. And then we have the crystal sequence, which of course creates the crystal spiral, and the sequence is just a pattern of doubling, so it's a very predictable mathematical pattern, yet prime 7 shows up here as well. And of course we have Euler's constant, which is used for a lot of calculus and differentials and trigonometry. In all these patterns, we can see how treating them like they're one long number, or even in the ones that are infinite decimals, which are supposed to be one long number, they can also be perceived to be overlaps of multiples of 7. And this is scale symmetry because they're all similar in the fact that they're multiples of 7, and there's different scales as in the number of digits that are in each one. And as we saw, it's always 6 digits or less. Now there have been times, very rarely, where I've found 7 digits like that, but if so, the last digit was always a 7 or a 0. So in a way, it was just sort of restarting another cycle. And the reason that I believe they show up in this way is we're talking about symmetries and how these different prime numbers govern different numerical symmetries. And of course, symmetry is geometry. And when we think about geometry in the first 3 dimensions, it gives us 6 cardinal directions of possible growth based on axes. You have like up and down of the y-axis, left and right of the x-axis, and the forwards and backwards of the z-axis. Any other directional movement besides those that's moving outward from the center would really just be a combination of 2. So those are the 6 cardinal. But there's a 7th direction, which could be moving towards the center instead, within. And I sort of believe that's what plays into the 4th dimension, how it exists, is it's not necessarily beyond the 3rd dimension, as we've discussed before, but among it and within it. And we see that in these math examples, where you have 6 digits or less, and when they reach the 6 digits, it's almost like it's representing 6 cardinal directions of geometry, since it's appearing within symmetry, and symmetry is geometry. And then we use prime 7 within these patterns as a 7th direction to break them down and to make them smaller, and to reveal the overlap in the perception that they can be perceived as more than just one whole infinite number, actually multiple overlaps of 7, which takes an intangible idea like the infinite and puts it into the realm of possibility. Alright, and I think that's going to wrap up this portion of numerical symmetry. I'm sure we'll touch on it again in the future. There's a few other prime governors I did not share this time. But for the next episode, it's going to be episode 7. So we're going to talk about my favorite number and my life path number, prime 7. And its sort of strange existence within reality and how it really is pervasive in almost every aspect of reality that we've imagined. So look forward to that. It'll be dropping next Friday. As always, I appreciate everybody tuning in. If you don't already follow the J-Axis on Instagram, please check it out. I'm sure you'll enjoy it. And we'll see you next time. Thank you.